Lava is already one of the most dramatic things on Earth, but sometimes lava does things that go beyond dramatic and into genuinely bizarre. So today we're counting down 15 strange lava phenomena, the ones that break the rules, defy the expectations, and occasionally defy explanation entirely. Let's start with number 15, lava bubbles. When most people picture a volcanic eruption, they imagine rivers of orange molten rock pouring down a mountainside. What they probably don't imagine are bubbles. But that's exactly what happens at certain lava lakes. The surface of the lava, which has cooled just enough to form a thin, dark skin, begins to inflate. Slowly at first, then faster. The dome expands outward, sometimes reaching about 15 or 20 feet across, roughly the size of a small garden shed, until the pressure inside exceeds the strength of that cooling surface skin. And then it pops. The bubble collapses back into the lava in a spray of incandescent fragments that arc high into the air, glowing orange against whatever light is left in the sky. The whole cycle, from inflation to detonation, can take anywhere from a few seconds to several minutes. Then another dome begins to form, and another. What's driving it is gas. Volcanic lava is saturated with dissolved gases, water vapor, carbon dioxide, sulfur dioxide, and as the lava rises toward the surface, the pressure holding those gases in solution drops. They want out. The skin of cooler lava on the surface traps them temporarily, and the result is something that looks less like geology and more like a pot of something extremely thick, extremely hot, and extremely dangerous coming to a boil. The lava itself is around 1,100 to 1,200 degrees Celsius. That's roughly the temperature at which steel begins to melt. These bubbles have been filmed extensively at Erta Ale in Ethiopia and at Kilauea in Hawaii, two of the most persistently active lava lakes on the planet. The footage, when slowed down, is one of the most hypnotic things you'll find in any corner of the internet. A glowing dome of liquid rock the size of a garden shed, inflating in slow motion, then shattering outward in a burst of fire. But honestly, most people aren't watching lava bubble videos for the thermodynamics. They're watching because a sphere of molten rock is quietly inflating like a balloon and then exploding. And that's a completely reasonable reason to watch. It's one of those things where the science and the spectacle are pulling in exactly the same direction, both of them pointing at something that should not, by any ordinary logic, be sitting calmly on the surface of the earth doing that. 14. Pele's hair and Pele's tears. During a major eruption in Hawaii, the wind picks up tiny threads of molten lava and stretches them, the way you'd pull taffy, except the taffy is liquid rock at around 1,000 degrees Celsius, and the pulling happens in milliseconds. What comes out the other end are strands of volcanic glass finer than human hair, sometimes thinner. A single strand can be less than half a millimeter across and stretched to lengths of 2 meters, about the height of a door frame, made entirely of glass, floating on the wind. These are called Pele's hair, named for the Hawaiian goddess of volcanoes. The tears are different. Those are the droplets that didn't stretch. Small, teardrop-shaped beads of volcanic glass that solidify mid-air and fall like a strange, dark rain. Together, Pele's hair and Pele's tears are what happens when an eruption column meets a strong enough wind and the lava doesn't know which direction to go. Both travel. That's the part that catches people off guard. During significant eruptions at Kilauea, strands of Pele's hair have been found coating rooftops, cars, and vegetation dozens of miles from the vent. The wind carries them. They're light enough to stay aloft for a long time, sharp enough to cause irritation on contact, and delicate enough that most of them shatter on landing. So they're everywhere and almost nowhere at once. The name itself comes from native Hawaiian tradition, in which Pele is the creator of the Hawaiian Islands, a figure of immense power and, depending on the story, considerable temper. The hair and tears are hers. The eruption is personal. And then there's the postal situation. The National Park Service at Hawaii Volcanoes National Park receives, on a regular basis, packages from tourists who visited, picked up a strand of Pele's hair or a small piece of volcanic rock as a souvenir, took it home, and then mailed it back, with a letter. The letters typically describe a run of bad luck that began shortly after the rock left the island. Job losses, car accidents, relationship breakdowns, illness. The park has a name for it. They call it Pele's curse. The curse isn't actually an ancient Hawaiian tradition. Researchers have traced it back to mid-20th century tourist literature, possibly invented to discourage people from removing rocks from the park. Whether it worked is debatable. The packages keep arriving. What isn't debatable is that somewhere right now, in a post office or a park ranger's office in Hawaii, there is a cardboard box containing a small piece of volcanic glass and a handwritten apology addressed to a goddess. That detail, more than the glass threads, more than the tears, more than the wind carrying fragments of an eruption across dozens of miles, is the one that stays with you. Lava tree molds, number 13. In the rainforest near Hawaii Volcano on the Big Island of Hawaii, there's a state park where you can walk among the ghosts of trees. Not stumps, not charred remains. Hollow stone cylinders standing upright in the forest, some of them taller than a person, each one the exact shape of a tree that no longer exists. The tree is gone. The rock remembers it anyway. Here's what happened. When a lava flow moves through a forested area, the molten rock, which can be around 1,200 degrees Celsius, surrounds and encases the trunks. The outer surface of the lava that touches the tree cools rapidly on contact. It hardens. Meanwhile, the tree itself ignites and burns away from the inside of that hardening shell, and the rest of the lava flow drains downhill and keeps moving. What's left behind is a standing cylinder of solidified basalt with a hollow center, a perfect mold of the tree that was there. The texture of the bark is sometimes preserved in the rock, the diameter of the trunk, the slight lean of the tree before it was hit. These are called lava tree molds, and the park where you can see them, Lava Tree State Monument near the town of Pahoa on the Big Island, contains dozens of them clustered across a few acres of forest floor. Some reach 2 or 3 meters in height. Walking through them feels less like a geology lesson and more like wandering into a place where something was erased in a hurry and the erasure wasn't quite complete. The molds form best when the lava flow is fast moving and the trees are large enough to cool the outer lava before the flow drains. Smaller trees tend to get consumed entirely. The ones that leave molds behind are the ones that were substantial enough to matter. Old-growth ohia trees, in many cases, some of them decades or centuries old before the lava arrived. So the molds are a record not just of the eruption, but of the forest that existed before it. The size of each cylinder tells you how old the tree probably was. The spacing between molds tells you something about how the forest was arranged. It's a negative archive, information preserved in absence rather than presence. The lava that formed them came from Kilauea's East Rift Zone. The park was established in 1955 after eruptions in that decade left a fresh field of molds accessible enough to protect and visit. Each hollow cylinder is a monument to something that was alive, that was swallowed by fire in a matter of minutes, and that left behind only the shape of itself, pressed into rock, standing in the forest, waiting for nobody in particular. At number 12, the blue flames of Kawah Ijen. On the island of Java in Indonesia, there is a volcano where the lava appears to burn blue, not orange, not red, not the yellow-white of an intensely hot fire. Blue, the color of a gas burner on a kitchen stove scaled up to the size of a building and burning against a black volcanic sky. The correction matters here. The blue flames aren't blue lava. The lava itself is the same temperature and color as lava anywhere else. What's burning blue is sulfuric gas, sulfur dioxide and hydrogen sulfide seeping up through cracks in the volcano surface, igniting on contact with the oxygen in the air, and producing flames that can reach 5 meters high, about the height of a 2-story house in blue fire on the side of an active volcano. At night, during the day, Kawah Ijen looks dramatic but comprehensible. A turquoise crater lake, the largest highly acidic crater lake on Earth, sitting inside a caldera in East Java. The lake's pH is close to 0. It's essentially a natural reservoir of sulfuric acid, roughly 250 meters deep and about a kilometer across. But at night, the mountain changes entirely. The sulfur gas ignites, and the flanks of the crater glow blue against the darkness. A mountain burning the wrong color, looking less like geology and more like something from a different set of physical rules entirely. And through all of this, people are working. Miners have been extracting sulfur from Hawaiian for generations. They descend into the crater at night, break off chunks of solidified yellow sulfur from around the vents using iron bars, load the chunks into woven baskets, and carry those baskets back up the crater rim and down the outer slope to a weighing station. A full load weighs between 70 and 90 kilograms, roughly the weight of an adult person, carried on the shoulders up a steep volcanic crater wall in sulfurous air past blue fire. They do this for a few dollars per load. Some make 2 trips a day. The sulfur they extract is used primarily in the sugar refining industry to bleach sugar white. The miners wear basic masks if they wear anything at all. The long-term health consequences of working regularly in that air are severe. Several miners have worked the crater for decades regardless. Hawaiian has been studied extensively by volcanologists and photographed by everyone who can get there. The blue fire has appeared in documentaries, photography books, and travel features. It is one of the most visually extraordinary things an active volcano produces anywhere on Earth. The miners were there before the photographers arrived. They're still there now. 11. Old Doinyo Lengai, Tanzania. Every volcano on Earth erupts lava that glows red, orange, or yellow. Every volcano except one. Old Doinyo Lengai sits in the Gregory Rift in northern Tanzania, rising about 3,000 meters above sea level at the southern end of Lake Natron. From a distance, it looks like any other stratovolcano, steep-sided, symmetrical, scarred by old flows. But what comes out of it is unlike anything else produced by any other volcano on the planet. The lava is natrocarbonatite, not silicate lava, which is what every other volcano on Earth produces. This lava is made primarily of sodium and potassium carbonate, essentially a molten form of mineral salts. And because of that radically different chemistry, it erupts at temperatures between 500 and 600 degrees Celsius. That sounds hot. For lava, it's barely warm. Standard basaltic lava erupts at somewhere between 1,000 and 1,200 degrees Celsius, roughly double. That temperature difference changes everything about how it behaves. At 500 degrees, natrocarbonatite lava is dark brown to black when it erupts, not the glowing orange-red that lava is supposed to be. It's cool enough, relatively speaking, that it doesn't emit visible light in daylight. You could be standing near an active flow and not immediately recognize it as lava at all. It's also extraordinarily fluid, thinner than water at eruption temperature, flowing faster than a person can walk across flat ground and spreading in thin sheets rather than thick tongues. And then it does something no other lava does. It reacts with the atmosphere. Within hours of exposure to air and moisture, natrocarbonatite lava begins to lighten in color. Within days, it turns white or pale gray, the dark volcanic rock bleaching itself in the open air. The flanks of Old Doinyo Lengai are streaked with white flows that look more like limestone or dried salt than anything volcanic. A geologist seeing photographs without context might not immediately place it. The Maasai, who have lived in this region for centuries, call it the Mountain of God. It sits at the edge of one of the most alkaline lakes in the world, Lake Natron, whose waters are so caustic they can chemically burn the skin of animals not adapted to it, yet support massive breeding colonies of flamingos that nest on its shores in numbers reaching over 1 million birds. Old Doinyo Lengai erupted significantly in 2007 and 2008, sending flows down its flanks and reshaping its summit crater. It's been intermittently active since. No other volcano on Earth produces this lava. Not one. The chemistry requires a very specific set of conditions in the mantle below. Conditions that, as far as geologists can determine, exist in only this one place. A mountain that decided to be the exception to every rule volcanoes follow, sitting quietly above a pink lake in the East African Rift, still making up its own geology as it goes. Number 10. Lava coils and spirals. Sometimes lava forms a perfect coil. Not approximately coiled, not vaguely curved. A tight, rope-like spiral, wound with the kind of geometric precision that looks less like something a volcano produced and more like something a person left behind. The mechanism is straightforward once you know it, but the result still looks wrong. When a lava flow moves across a surface, the outer skin cools and stiffens faster than the interior. If the flow then slows, stops, or gets deflected by an obstacle, by a change in slope, by the front of the flow backing up against itself, the still liquid interior keeps pushing forward inside that stiffening shell. The crust buckles and rotates. The whole thing coils, the way a garden hose coils when you drop it on the ground, except this hose is made of rock and was liquid 30 seconds ago. The resulting coils can range from a few centimeters across to over a meter in diameter. They're found on land, particularly on Pahoehoe lava flows in Hawaii, where the smooth, ropey surface texture creates ideal conditions, and on the ocean floor, where slow-moving submarine lava behaves similarly under the pressure and cold of deep water. Pahoehoe itself is worth a moment. It's one of the two main types of basaltic lava flow, the other being AA, which is rough, clinkery, and moves in a tumbling mass of jagged fragments. Pahoehoe is the opposite, smooth, glassy, flowing in sheets and lobes with a skin that wrinkles and folds as it moves. The surface of a Pahoehoe field looks like coiled rope, or rumpled fabric, or the skin of something that was moving and then stopped. Lava coils are an extreme version of that same process, the wrinkling taken all the way to a full spiral. What makes them genuinely strange is the precision. Researchers who photograph lava coils in the field note that the geometry is often nearly perfect. Consistent radius, consistent spacing between the wound layers. The physics of cooling and viscosity produce a result that looks engineered. It isn't. It's just what happens when a fluid with those particular properties, cooling at that particular rate, runs out of room to go straight. Lava coils have also been identified in orbital imaging of Mars. The same formations, same geometry, same rope-like texture appear on ancient Martian lava plains, which tells volcanologists that the process producing them is consistent enough to replicate on another planet entirely. Under different gravity, different atmospheric pressure, different everything, the coil doesn't care where it is. Given the right conditions, it makes itself. On Earth, finding a well-formed lava coil in the field is considered a minor event worth documenting. They're not rare exactly, but a perfect specimen is uncommon enough that volcanologists photograph everyone they encounter. A small, precise spiral of rock sitting on a lava plain that the planet assembled for no reason other than physics. 9. Volcanic lightning, or dirty thunderstorms. Thousands of lightning bolts, generated not by a storm system, not by clouds building over hours, but by a volcano in minutes inside its own eruption column. Volcanic lightning is exactly what it sounds like, and somehow still more extreme than that description prepares you for. When a volcano erupts explosively, it sends a column of ash, rock fragments, and gas surging upward at enormous speed, sometimes reaching altitudes of 10 to 20 kilometers, high enough to punch into the stratosphere. That column is not electrically neutral. The violent collision of ash particles, ice crystals, and rock fragments within the plume strips electrons from their atoms, creating regions of strong positive and negative charge separated by distance. When the charge difference becomes large enough, it discharges. The result is lightning, not borrowed from a passing thunderstorm, but generated entirely by the eruption itself. The bolts can be massive. During the eruption of Calbuco in Chile in 2015 and at Sakurajima in Japan, one of the world's most active volcanoes, which produces volcanic lightning regularly enough that it's been studied systematically, researchers recorded thousands of lightning strikes within single eruption events. Some bolts traveled several kilometers through the ash column. Others flickered in tight clusters near the vent, small and rapid, like static discharge scaled up to a terrifying degree. There are actually two distinct types. The first appears almost immediately at the vent when the eruption begins. Small, fast discharges caused by the fracturing and collision of rock and magma right at the point of eruption. The second type develops higher in the column as the plume rises and ice forms around ash particles, mimicking the charge separation process inside a conventional thunderstorm. Same electrical physics, completely different cause. Filmed clearly at Sakurajima and at the eruption of Eyjafjallajökull in Iceland in 2010, which grounded air travel across Europe for 6 days and introduced a generation of news anchors to a word they could not pronounce. Volcanic lightning has become one of the most documented and most studied phenomena in volcanology over the last 2 decades. High-speed cameras deployed near active vents have captured the discharge sequences in enough detail to distinguish between the vent-generated and plume-generated varieties in real time. If you're enjoying the video, drop a like and a comment. It really does help the channel out. The footage from Sakurajima in particular, a dark eruption column rising against a gray sky threaded through with rapid white bolts from base to summit, is one of the most visually extreme things geology and atmospheric physics produce together anywhere on Earth. But yeah, what stays with you isn't the footage, it's the mechanism, a volcano generating its own weather, its own electrical storm. Building a thunderstorm from scratch out of nothing but rock and pressure and speed, in the time it takes to walk across a room. 8. Lava entering the ocean. When an active lava flow reaches a coastline and pours into the sea, the ocean doesn't stop it. Not immediately. Not cleanly. What happens instead is a collision between two systems that have no interest in accommodating each other, and the result is one of the most visually extreme things geology produces at the surface of the Earth. The lava, arriving at around 1,100 degrees Celsius, hits seawater and the water flash vaporizes on contact. Instantly. The steam explosion is violent enough to shatter the outer skin of the lava into fine black fragments, and those fragments get carried upward in the plume along with the steam. That plume has a name, LAZE. It stands for lava haze, and it is not simply steam. It contains hydrochloric acid, formed when the seawater's chloride reacts with the heat, and tiny shards of volcanic glass. Particles fine enough to be inhaled, sharp enough to lacerate lung tissue. LAZE is classified as a genuine health hazard. Standing downwind of an ocean entry point without protection is not a mistake people make twice. Below the surface, something different is happening. The lava that makes it into the water without being immediately shattered gets quenched by the cold, cooling so rapidly on the outside that it forms a glassy skin while the interior stays molten. The pressure of the water above prevents the steam from expanding explosively, so the lava inflates into bulging lobes, stacked on top of each other as the flow continues. These are pillow lavas, and they build up on the ocean floor in formations that can extend for kilometers, layer upon layer, each one a record of a separate flow event. At the shoreline itself, the entry point glows white and orange through the steam, a curtain of vapor backlit by molten rock, with new land forming in real time beneath the surface. Hawaii has gained measurable coastline this way. The 2018 eruption of Kilauea's Lower East Rift Zone added roughly 3.5 square kilometers of new land to the Big Island, an area roughly the size of 500 football fields, built entirely from lava flows entering the ocean over a period of several months. That new land is not stable immediately. The benches that form at ocean entry points are built on unconsolidated lava fragments and can collapse without warning, dropping sections the size of city blocks into the sea. The United States Geological Survey has documented multiple bench collapses at Hawaiian entry points, some of them generating small local tsunamis. So the coastline is growing and collapsing simultaneously. New land appearing on one side of the bench, chunks of it falling back into the ocean on the other. The net result is land gained, but the process is not orderly. The Earth adding to itself at the waterline in real time, and occasionally taking some of it back. At number 7, columnar basalt. Cooling is supposed to be a slow, disorganized process. Rock solidifying from lava should crack randomly, the way a dried up riverbed cracks, or the way old paint splits in irregular, unpredictable patterns. And yet, under the right conditions, cooling basalt does something else entirely. It cracks into columns. Hexagonal columns packed so tightly together they share walls, extending downward through the rock for tens of meters with a geometric regularity that looks less like a natural process and more like something that was planned. The mechanism is well understood. As a thick lava flow or lava lake cools from the top down, it contracts. That contraction generates stress across the surface, and the stress resolves itself through cracking. The mathematics of stress distribution on a contracting surface, the same mathematics that govern how mud cracks as it dries, consistently produces a hexagonal network as the most efficient solution. 6-sided cells minimize the total length of crack needed to relieve the stress across the whole surface. The rock is, in a sense, solving an optimization problem. The answer is always hexagons. Those surface cracks then propagate downward as cooling continues, extending into the rock at a rate determined by how fast the heat is escaping. The result is a field of columns, each one a hexagonal prism, standing vertically, often 30 to 40 meters tall, packed edge to edge across an area that can stretch for kilometers. The Giant's Causeway on the northern coast of Northern Ireland contains roughly 40,000 of these columns, the tallest reaching about 12 meters, about the height of a 4-story building, stepping down from the cliff face into the North Atlantic in a formation so regular it generated genuine folk mythology. The columns were attributed to the Irish giant Fionn mac Cumhaill, who supposedly built a causeway to Scotland. The actual basalt is around 60 million years old, formed during a period of intense volcanic activity as the North Atlantic began to open. Fingal's Cave on the Scottish island of Staffa is made of the same basalt, from the same eruption sequence, now accessible only by boat and extending into a sea cave where the columns form the walls and ceiling. The composer Felix Mendelssohn visited in 1829 and wrote an overture inspired by it. The acoustics inside, the columns acting as a kind of resonating chamber for the sound of the sea, apparently contributed. Devil's Postpile in California, Svartafoss Waterfall in Iceland, the organ pipes on the slopes of Mount Cargill in New Zealand. The same formation, the same geometry on every continent, in every climate where thick basaltic lava has cooled slowly enough for the columns to form fully. 40,000 interlocking hexagonal columns, each one the answer to the same equation the rock solved 60 million years ago, still standing at the edge of the sea. The geometry hasn't changed. It never does. 6. Pillow lava, and the volcano you'll never see. Most people think of lava as something that flows down the side of a mountain. Visible, dramatic, accessible enough to photograph from a helicopter or watch from a viewing area behind a rope barrier. But the vast majority of volcanic activity on this planet doesn't happen on land at all. It happens at the bottom of the ocean, in the dark, under kilometers of water, and it has been happening continuously at thousands of locations simultaneously for as long as the Earth has had oceans. The mid-ocean ridge system, the network of underwater mountain ranges that runs through every ocean basin on Earth, connecting at the seams between tectonic plates, is the most volcanically active feature on the planet. It stretches for roughly 65,000 kilometers. That's 1.5 times the distance around the Earth at the equator. Along its entire length, lava is erupting from the seafloor on a near-continuous basis, building new oceanic crust from below. None of it glows orange. None of it is visible from the surface. And the form it takes is completely different from anything that erupts on land. When lava erupts into seawater under high pressure and near freezing temperatures, the outer surface quenches, solidifies, almost instantly, forming a glassy skin. But the interior stays molten and keeps flowing, inflating the skin outward into a rounded lobe. Then another lobe pushes out from that one. Then another. The result is a stack of smooth, bulging forms, each one roughly the size and shape of a large pillow or a bread roll, piled on top of each other across the ocean floor in formations that can extend for kilometers in every direction. These are pillow lavas. They're the most abundant type of lava on Earth by volume, and almost nobody has ever seen them in person. Submersible expeditions, beginning with the deep-sea research programs of the 1970s and continuing through to remotely operated vehicle surveys today, have filmed pillow lava formations at the East Pacific Rise, the Mid-Atlantic Ridge, and dozens of other sites. The footage is genuinely strange. Rounded black lobes stacked in the darkness, some still warm enough to register on thermal sensors, surrounded by the kind of absolute silence that exists only several kilometers below the ocean's surface. Pillow lavas also form the geological record of ancient sea floors. When oceanic crust gets subducted or thrust up onto land during tectonic collisions, the pillow lavas come with it. Sequences of pillow lava are exposed in Cyprus, in Oman, in Newfoundland. Ancient ocean floors now sitting on dry land, their rounded lobes still intact after hundreds of millions of years. Over 70% of all volcanic output on Earth is produced this way, invisibly, continuously, in water cold enough to solidify the outer surface of lava in seconds, at depths where the pressure alone would crush an unprotected human being flat. The largest volcanic province on Earth lies beneath the Pacific Ocean. Most of it has never been directly observed. Lava tubes. Number 5. Beneath the surface of Hawaii's Big Island, there are tunnels wide enough to drive a bus through. Some of them stretch for miles in near-perfect darkness, their walls smooth and glassy. Their floors flat where ancient lava once pooled and drained. They are not caves in the conventional sense, not carved by water, not formed by geological collapse. They were built by lava, from the inside out, and then abandoned. Here's how it works. When a lava flow travels a long distance from its source, the outer surface cools and hardens while the interior stays molten, insulated by the very rock it just created. The hardened shell becomes a roof. The liquid lava inside keeps flowing beneath it, draining downhill toward the ocean or pooling in low points. When the eruption stops or the supply of lava is cut off, the interior drains out and leaves behind a hollow tube, a tunnel with lava-sculpted walls, sometimes circular in cross-section, sometimes more irregular, depending on how the flow behaved. The Kazumura cave system on the Big Island of Hawaii is the longest and deepest known lava tube on Earth. It runs for approximately 66 kilometers, roughly the driving distance from Washington, D.C. to Baltimore, and descends more than 1,000 kilometers in elevation from its upper entrance near the summit of Kilauea to where it exits near the coast. Sections of it are tall enough to walk through upright, others require crawling. The walls in places are coated with lava stalactites, drips of molten rock that solidified mid-fall when the tube was still active, hanging from the ceiling like frozen rain. Lava tubes preserve their interiors remarkably well. The rock roof insulates the tunnel from surface weathering, from temperature swings, from erosion. Tubes that formed thousands of years ago look, in places, as though the lava drained out last week. And then, there's where this goes next. NASA and the European Space Agency have both identified lava tube formations on Mars and the Moon through orbital imaging. The same process, lava flowing under an insulating crust, draining out, leaving a hollow, operates under lower gravity on both bodies, which means the tubes that form there are potentially far larger than anything on Earth. Estimates based on imaging data suggest some lunar tubes could be wide enough to contain a medium-sized city. The reason this matters practically, a lava tube on the Moon or Mars would provide natural shielding from radiation, micrometeorite impacts, and extreme temperature swings, the three most immediate physical hazards for any long-duration human presence on either body. Engineers and space agencies are actively studying terrestrial lava tubes, including those in Hawaii and the Canary Islands, as analogs for what future explorers might shelter inside. A tunnel built by a volcano, abandoned for thousands of years, is now being mapped and measured as a potential blueprint for surviving on another world. The lava that made it is long gone. The architecture remains. 4. Obsidian, the sharpest material humans ever used. For tens of thousands of years, before metal, before ceramics, before any of the materials we associate with human technological progress, people were traveling hundreds of miles across difficult terrain to collect a specific type of volcanic rock. Not because it was pretty, because nothing else cut like it. Obsidian is what happens when silica-rich lava cools so rapidly that the molecules don't have time to arrange themselves into a crystal structure. The result is volcanic glass, amorphous, meaning structurally disordered at the atomic level, with no grain boundaries, no crystal planes, no internal structure for a fracture to follow. When obsidian breaks, the fracture propagates in a smooth, continuous curve called a conchoidal fracture. The edge it produces is not serrated, not irregular. It tapers to a thickness of around 3 nanometers, roughly 30 times thinner than the edge of a steel surgical scalpel. That number is not an approximation. 3 nanometers is close to the theoretical limit of sharpness for any solid material. Obsidian edges are sharp enough to cut individual cells rather than rupturing them, which means tissue on either side of the cut remains largely intact. Archaeologists have traced obsidian artifacts across entire continents using geochemical sourcing, matching the trace element signature of a tool to the specific volcanic deposit it came from. A spear point found in one location can be matched with high confidence to a source outcrop hundreds of kilometers away. The trading networks this implies were vast, organized, and operating tens of thousands of years before written records. Major obsidian sources in the ancient world included deposits in Anatolia, what is now Turkey, which supplied material across the entire ancient Near East. Obsidian from the Aeolian Islands off Sicily moved throughout the Mediterranean. In the Americas, sources in what is now Mexico supplied material to cultures across Mesoamerica for millennia. Wherever it existed, people found it, extracted it, and moved it. The flows themselves are visually striking. Obsidian doesn't look like basalt or pumice or any other common volcanic rock. It's glassy, jet black when pure, with a surface that reflects light like dark mirror glass. Some varieties contain gas bubbles or mineral inclusions that produce patterns. Snowflake obsidian, rainbow obsidian. But the pure black material is what most cultures sought for tools, and some surgeons still seek it now. A small number of surgeons in the United States and elsewhere use obsidian scalpels, typically hand-knapped blades mounted in conventional handles, for procedures where minimizing cell damage at the incision site is the priority. The blades are not commercially manufactured at scale. They are made by hand using the same knapping technique humans have used for 100,000 years by craftspeople who supply a niche surgical market. A material formed in minutes by a volcano, shaped by human hands for 100 millennia, still sharp enough to be useful in an operating theater today. The volcano that made it didn't know what it was making. It never does. Number 3. Surtsey, the island that built itself. On the morning of November 14th, 1963, the crew of a fishing vessel working in the waters south of Iceland noticed something wrong with the sea. There was smoke rising from the surface, then steam. Then, as they watched, the water began to break apart from below. A new island was being born. What followed over the next 3.5 years was one of the most documented geological events of the 20th century. A submarine volcano erupting from the seafloor at a depth of around 130 meters had finally built its cone high enough to breach the surface. The initial eruption was explosive. Seawater mixing with magma produces violent steam-driven blasts called Surtsean eruptions, named for this event, sending columns of ash and steam hundreds of meters into the North Atlantic sky. The island grew fast. Within days, it was large enough to stand on, though the surface was still erupting and largely unstable. Within weeks, it had a recognizable shape. By the time the eruptions finally ceased in 1967, Surtsey covered approximately 2.5 square kilometers and rose about 150 meters above sea level, roughly the height of a 40-story building assembled from nothing in the middle of the ocean in under 4 years. And then scientists sealed it off. Access to Surtsey has been restricted to authorized researchers since its formation. No tourists, no casual visitors. The entire island is a natural laboratory for a single question. How does life colonize a sterile surface? When Surtsey emerged, it was completely bare. New rock, no soil, no organisms of any kind. Researchers have monitored it continuously since, documenting every arrival. Bacteria came first, carried on the wind. Then mosses, then seabirds who landed, nested, and left behind droppings that began building soil. Seals arrived, then plants whose seeds had been carried in bird intestines. Within a few decades, a functioning ecosystem was assembling itself on rock that hadn't existed when the 1960s began. The island is also shrinking. Wave erosion has reduced Surtsey from its peak size to around 1.5 square kilometers today, and the process continues. The volcanic rock is relatively soft and the North Atlantic is not gentle. Researchers estimate that Surtsey will be reduced to reef below the waterline within a few centuries. The entire island, its ecosystem, its scientific record, return to the sea. So, the experiment has a deadline. The research program is not open-ended. Every field season on Surtsey is conducted with the awareness that the island itself is temporary, a brief interruption in the ocean's surface that will eventually close back over. An island that erupted from the North Atlantic in fire and steam, sealed itself off from human interference, built a functioning ecosystem from bare rock in decades, and is now slowly returning to the seafloor it came from. One of the most carefully monitored and scientifically consequential pieces of ground on the planet, about the size of a large city park. 2. Kilauea, 35 years of continuous eruption. 35 years. Not 35 years of occasional activity, not 35 years of monitoring a restless volcano. 35 years of continuous eruption from 1983 to 2018, making Kilauea's Pu'u vent one of the longest-lived rift zone eruptions ever recorded on Earth. Kilauea sits on the Big Island of Hawaii, on the southeastern flank of the much larger Mauna Loa, and it is not a dramatic cone-shaped volcano in the popular imagination sense. It's broad, low, shield-shaped, built from thousands of overlapping lava flows rather than explosive eruptions. The lava it produces is fluid basalt, and it travels. During the Pu'u eruption, lava flows extended from the vent all the way to the coast, a distance of around 18 kilometers, filling valleys, crossing roads, and reaching the ocean in a near-continuous process for decades. The volume is difficult to hold in the mind without a reference point. Over the course of the Pu'u eruption, Kilauea produced enough lava to pave a 4-lane highway stretching from New York to Los Angeles and back. Not a rough estimate. That's the order of magnitude of what came out of one vent over 35 years. And then in 2018, the eruption changed character entirely. The Pu'u cone collapsed in late April of that year, and within weeks, new fissures opened in Kilauea's Lower East Rift Zone, directly through residential neighborhoods in the Leilani Estates subdivision on the Big Island, not on a remote volcanic plain, through streets, yards, and driveways. 24 fissures opened across the subdivision. Lava fountains reached heights of over 50 meters. Entire streets were buried under flows that in some places reached 15 meters deep and about the height of a 5-story building in solidified lava where houses used to be. Over 700 homes were destroyed, around 30 square kilometers of land were buried. The ocean entry at Kapoho Bay, a sheltered bay that had existed for centuries, used for swimming and snorkeling, was filled in completely within days. It no longer exists. In its place, Kilauea added roughly 3.5 square kilometers of new land to the Big Island coastline, built entirely from the material that had just buried the bay. The displacement was significant. Thousands of residents left, many permanently. The community of Lanapuna Gardens was entirely destroyed. Vacation land, a subdivision near the coast, was buried. Kilauea erupted again in 2020, filling the summit crater lake with lava. Again in 2021, again in 2023. Each eruption different in character and location from the last. The volcano shifting its behavior, redistributing its energy, finding new pathways. The Hawaiian Islands exist because of Kilauea and the hotspot beneath it. Every island in the chain was built by the same process over millions of years, as the Pacific Plate moved slowly northwest over a fixed point of intense volcanic activity. The Big Island is the youngest. It is still being made. What was lost in 2018, the homes, the bay, the neighborhoods, is now part of the geological record of an island that isn't finished yet. The lava that buried Kapoho Bay is now coastline. In a few thousand years, it will be soil. 1. Nyiragongo, the world's most dangerous lava lake. 2 million people live within reach of it, not within reach of a volcano in the abstract, distant geological sense. Within reach of a lava lake that drained almost completely in under an hour the last time it decided to move. Nyiragongo sits in the Virunga Mountains in the Eastern Democratic Republic of Congo, about 20 kilometers north of the city of Goma, a city of over 2 million people built on the solidified lava of previous eruptions. The volcano rises to around 3,470 meters. At its summit, inside a steep-walled crater, sits the largest and most active lava lake on Earth. The lake has been present in some form for most of the last century. It glows. On clear nights, it illuminates the clouds above the crater from below, a red pulse visible from the city. In January 2002, the lake drained. Not slowly, not in the gradual, manageable way that volcanologists can track and warn against. Fissures opened on the southern flank of the volcano, and the lava lake emptied through them in a matter of hours, sending multiple flows racing downhill toward Goma at speeds clocked at up to 60 kilometers per hour, faster than most people can drive on a city street, across terrain that includes neighborhoods, markets, and the main road to the Rwandan border. The flows reached Goma. They crossed the runway of the airport. They buried the center of the city under lava up to 2 meters deep, roughly the height of a doorframe, in solid rock where streets had been. Around 100 people died in the eruption and its immediate aftermath. Around 400,000 were displaced, many of them crossing into Rwanda in one of the largest single volcanic displacement events in recorded history. The lake refilled within weeks. It has been full since. Nyiragongo's lava is unusually dangerous for a specific chemical reason. It is exceptionally low in silica, which makes it among the most fluid lavas on Earth, thinner than most other basaltic lavas, capable of flowing at extreme speeds down the steep flanks of the volcano with almost no warning. The 2002 event was not the first. A similar drainage in 1977 killed an estimated 600 people, with flows that reach speeds of up to 100 kilometers per hour in places, faster than highway traffic. The volcano erupted again in May 2021, sending flows toward Goma before stopping at the city's edge. Thousands evacuated. The flows halted. The lake, again, refilled. Monitoring of Nyiragongo is conducted by the Goma Volcano Observatory, operating under chronic underfunding and in one of the most geopolitically complex regions on the planet. The scientists who watch it work with equipment that is frequently inadequate for the task of monitoring a volcano of this behavior and this proximity to this many people. The lake is full now. It has been for years. It sits at the summit, glowing, 2 kilometers above a city that was partially buried by it within living memory. It is still very much capable of opening up and pouring itself across the land whenever and wherever it decides that the time has come. If you thought lava was strange, wait until you see our video on the world's most extreme volcanic eruptions ever recorded. Click here, and I'll see you over there.